The delay. So our next speaker is Jacob Faibussowitsch. He's a student who worked on PETSc. He fell into our trap, and he's been doing a lot of really great work updating our communication models and interaction with both GPUs and C++ in general, and he's going to talk to us about his asynchronous work. Thank you, Jacob.
Thank you, Toby. So yeah, my name is Jacob, and I will be talking about how to make working with asynchronous data on the GPU and how, the challenges that this presents and kind of how PETSc can help you deal with that. But first, I want to start off with some bad news. And that is, unfortunately, that all of your carefully crafted GPU code is horrendously slow. And it's through no fault of your own, but that's simply how it is. The common, paradigm is that the CPU is like an old wizened master. He can do many things very quickly, very complicated things, but he only has so many hands. And if he needs to do a lot of things, you turn to the GPU, which is more like a factory. But just like a factory, it has the same drawbacks and limitations in the sense that you have this huge startup cost. You constantly need to supply with this pipeline of work, and keeping up that pipeline is difficult, especially when the actual work that you're doing is not very compute intensive, as it very often is in scientific computing. Usually you're waiting for memory or other prior dependencies, and it turns out it's very difficult to actually keep the GPU saturated long enough or really full enough for it to really pay off unless the problem is enormous. So ultimately this results in you have performance left on the table and you want to recapture that. So if you don't believe me, I'll show you an example of it. This is pulled from your own code, believe it or not. And this is your prototypical how to normalize a vector. And as you can see, you do the vec norm, and the vector might be on the GPU, but at the end of the day, right, it computes the singular value that it then has to schlep up all the way back to the CPU, only for you to do a single scalar operation, and then the whole thing continues, and you use it in your vec scale. But ideally, all of this really should be done on the GPU, right? The fact that we need to stop the entire device, synchronize, communicate over, external hardware is extremely wasteful, and ideally you'd want to do this, we'll keep it on the device. So before we dive into that, what exactly is a GPU stream? Well, as was kind of touched on a little bit earlier, a GPU stream is essentially morally equivalent to a thread. And so it has the same kind of benefits and drawbacks. So if you launch or do something on a GPU thread, it's equivalent to launching a GPU stream. It's equivalent to launching a thread that does that work. Communication is handled by these essentially events, but under the hood there's the same kind of semaphores, condition variables, that kind of stuff. But it also comes with the same drawbacks. It's very easy to shoot yourself in the foot with these things. If you have some kind of data race dependencies with threading, it's exactly the same thing with GPU streams, right? You can have a deadlock hazard. Suppose two streams are trying to operate on the same thing, and they're trying to see if the value is some whatever. You have a race condition hazard, read after write, all this kind of stuff. So in general, they're quite complicated. And luckily, everybody decided on pthread as the global kind of threading API, so surely all of the vendors have agreed on a single implementation for streams. Of course, this is not the case. Everybody has their own flavor of it. They all do the same things, but they're all called different things. So in an effort, of course, to reduce this wrapping nightmare and all of these different names, we've come up with our own name. But ultimately, PETSc device context is a lot more than just a stream. It also helps to wrangle the different device libraries, make sure they play nice together. Bottom line is, the PETSc device context is the ultimate, the how, what, when, and where. It'll determine the device that the thing runs on, the stream that it runs on. If you need a Kubla's handle, it'll make sure that is properly set up using that stream, all the good stuff. So back to our original problem, how can we make this asynchronous using not just PETSc device context, but this new object, this PETSc managed memory? Well, as you can see, the first line, you retrieve this device context. This will create one if it doesn't exist yet, or get the current one if it does exist. Then you do this vec norm async, right? The value is computed directly in device memory. You're no longer writing to a CPU scalar. It means you don't have to copy it back up. The resulting operation right here is actually done entirely on the device, and it's symbolically represented, and it's essentially like a future, this managed real. And this supports any arbitrary expression, so including all the PETSc math. You could do PETSc sign, whatever, or even std sign if you'd want to. It's completely composable. Any kind of mathematical operation on these scalar values, you can just write it exactly as it is. In fact, so here I have this eval. This is just a way to attach the device context or the stream to that expression. You can drop it entirely. It'll just do it on the null stream, so fully synchronous. The point here is that this is very easy code to read and write, but does these things on the GPU. And then finally, you have this ability to await your results, right? This is the main difficulty with writing asynchronous code in a library context, because you, the user, when you call vec_scale, you expect by the time that function returns that that vec_scale is done, that you can inspect the array and modify it. But of course, it's very hard to square with the GPU framework, where ideally you want to launch it, and then at some point when it's done, come and get it. So you either need a way to catch the work that you've kind of thrown, right? You need a way to synchronize for it, or you need a way of saying, do this after that. And this does both. So let's get a little bit more complicated. One stream is nice. Of course, you'd want to be able to use multiple streams. Now, in this case, it doesn't make any sense, right? The data dependencies are exactly, you'd only ever want to use one stream, but just kind of as a play thing, let's try and see if we did multiple streams. So at a very first glance, you'd think, OK, so we have 3 streams. They're all operating kind of one after the other. Where is all the synchronization code, right? Surely this must have been written by an intern, because clearly these are all race conditions waiting to happen. In fact, that is not true. So under the hood, PETSc will track all of the read and write dependencies between them, and it'll serialize the streams for you. Again, the goal here is to separate the actual underlying device, event, and stream stuff from the business logic. In this case, the business logic is normalizing the vector. You should just be able to say, do this part of the operation on this stream, figure out the dependencies for me. And in fact, that's what it does. So I also want to point out that this works across a regular API. So you see that vec_get array at the bottom that everybody else uses. That will know to automatically synchronize before it actually returns the host array. So this is completely safe. You can access CPU array afterwards immediately, right? So why is this useful? This allows incremental porting if you choose to use this API. And it also allows that if you have some user code callbacks that are doing whatever the user does with it, that it's completely safe on their end, as long as, of course, they use these accessors, which everybody does. So the point is, you can have your fancy asynchronous GPU code, and you can rest assured that, unless you really try, you cannot mess this up. Right, this is all fine and dandy, but how is the performance? So in order to measure the performance, I ported the classic KSB-CG to this new asynchronous framework. And then I did a couple of experiments, and specifically, I was solving the Laplace equation with varying size and density. You can see in the footer note exactly what I did. The point is, the matrix got bigger and it got slightly denser, because we want to see, OK, if the actual total amount of work per row is the same, but we add more rows, how does that, do we still scale the same way? And if more work is done per row, if our kernels are more actually compute intensive rather than memory intensive, does it still scale the same way? I also only did 20 KSP iterations. This is kind of for simplicity of comparison. And then, preconditioning was just Jacobi iteration because it's Jacobi preconditioning because it's just a diagonal scale. Ultimately, it was chosen because I had to change less code. And also important is that it's on one MPI rank. Multiple MPI ranks is a little tricky. And I'd be happy to talk about it after. when there's questions. But without further ado, the timing results here for the time to solution. So this is the total time that it takes for you to KSP solve and then synchronize the device. So in the sense that when you get the solution vector, it is ready and it is done. And see the blue lines here, it'll be a bit tricky to see the difference between all the blue lines, but I think the thing to focus on here is that all the blue represent all of main. So this is your current main branch that everybody knows and loves. This is your KSP-CG on main versus the new asynchronous branch running again the same KSP, but now it's all asynchronous on the GPU. Plotting the flops as well, it tells a very similar story. The asynchronous branch is consistently faster and more efficient than main. And I think it's a bit hard to see, so if instead we plot the ratio between the times, it's a bit more clear. So the way to read this graph is if y is greater than 1, that means that main is faster than the async. And if it's less than 1, that means that main is that percent slower, ratio slower than the async. Of course, those with their thinking caps on will have realized that it is never greater than 1. So the point here is that the asynchronous code is always faster. So at this very bottom level here, it's at 0.6. So that means main is 60% the speed of the async, or conversely, the async is 80% faster than main. But one thing to highlight is this region at the end, right? If it's so great and it's, if it's always so much faster, why does it converge to, essentially the same speed, right? Like main is at 90% of the async speed now. Well, if we look at the timeline here of this particular solve, you can see at the top here, this blue bar is the GPU utilization. This KSP solve is the time that I was plotting in the original plot. And you can see most of the time here is waiting on this CUDA stream synchronize. This is waiting for the entire KSP, the 20 iterations to complete. So if we enlarge it a bit, you'll see that the vast majority of time is spent in matmult. And essentially, the point I'm trying to make here is that by the time the matrix gets so large, the time here is really dominated by your matrix multiplication time. So any kind of speed up that you get from async well, the measured speed up is proportionally smaller because everybody is actually just waiting on these huge matmult kernels. But another thing to note here is that all of these ticks at the left here are the actual PETSc calls, in the sense that these are all of your vec axps, whatever. So you'll note that this is essentially a fifth, maybe a sixth of the time that it takes for this huge solve. So, I mean, all that time you're waiting on CUDA stream synchronized, suppose you have multiple KSPs you'd like to solve, right? Suppose you have some kind of block solve. If you can launch all of them on a different stream, in theory, they all overlap at the same time. Because again, this is the amount of, at this point, PETSc has returned from KSP solve, right? And it is just waiting on this CUDA stream synchronize that is outside. So, conclusion, key takeaways. The async is faster than main across the board. That is for both big problems and small problems. It is much faster if your problem is latency bound, right? If you're just constantly waiting on the GPU to give you the work back, but the work is small, then you're getting a lot of speed up because you can immediately launch the next kernel. But the speed up diminishes to some degree when you become work bound, right? You're just waiting on these kernels to complete because, again, it doesn't magically make you do less work on the GPU. It just makes the work that you do on the GPU more compact, right? Instead of waiting between kernels, they're right after each other. But of course, that also assumes that you don't have something else that you could be doing in the meantime. As I alluded to before, right, this is waiting for one KSP solve. But suppose you want to do multiple KSP solves. Then you can really, you can do them almost at the same time. And depending on how the device scheduler will schedule your kernels, you could potentially have two or multiple KSP solves running completely concurrently. And that will get you, well, I don't want to put a number on it, but it'll get you a far, far larger speed up, because now you're not running them sequentially. So future work, I have implemented the CG. There's a TFQMR implementation. And I'm putting the final touches on GMRes, because everybody likes GMRes. There's also the idea of, now that these things are asynchronous, and you no longer have the expectation that the work that you say runs immediately, you also have the ability as a library to kind of defer that. So suppose you want to do a vec scale and then a vec norm, right? In your normal synchronous code, you have to do the vec scale immediately, and you have to do the vec norm immediately. But with the asynchronous, because you, the user, have kind of given up this idea that the scale must happen immediately, you can kind of collapse those into one. And in fact, so I've implemented this where all the vec operations will, at runtime, automatically fuse if they can. But the benefits of it still are kind of under investigation, because as it turns out, people don't just do vector stuff, they also use matrices. And at that, it's a little bit more complicated. So it needs to have tight integration with MAT to really be useful. Yeah, so that is still under investigation. The other thing is, with the async stuff, is that there is currently no way to unlaunch a kernel. So suppose you've done your 10 k-speed iterations, but you only needed 5 because it's already converged by that point. The device can figure this out. And so you'd want to say, at some point on the CPU, I've launched these kernels, but maybe don't do them when you get there. So you can do this kind of when you write your own CUDA kernels, because you can have like a little flag that those kernels will check and say, OK, do I continue with the operation? But if you're using, for example, cuBLAS or RockBLAS, they don't have any such ability. So that would be exceptionally useful for library developers. Because again, this would allow us to reap the benefits of, we can launch all these kernels, but then we can kind of unlaunch them if we need to. So with that, I want to thank everybody for listening. If you'd like to check out the branch, if you're personally masochistic and like to read the code, you can do so there. The link is to the merge request is there. But I will open the floor to any questions.
Jacob, thank you. Exciting stuff. Any questions? Here we go.
So the main challenge is from synchronized to asynchronous scheduling, right? So is there any chance of inaccuracy or higher level of inaccuracy by doing asynchronous execution?
I'm sorry, could you repeat that?
The chance of increasing inaccuracy in result?
No. So the point here is that essentially the dependencies are tracked for you. So there is no race condition to any of these. So it's as if they executed immediately in that order,
so the
but
last
it's deferred.
commented out can also be uncommented, right? The
Yeah,
very last line that
it is. You don't need it. That's the point.
Thank you.
Question in the back from Justin. 1 minute.
Hey, Jacob. Really interesting talk. Thanks. So I just have a very, very quick question. So are you open to the idea of using a vendor version of these conjugate gradient solvers? Because, like, for example, AMD, we have a solver package called Rockolution, and we do implement a CG and, I believe, GMRes, and we do very similar work where you do this asynchronization, where you fuse like these operations. So I guess maybe this is just a question for everyone in general. Like, are you guys open to using our work?
I guess the point of these changes is that we can take essentially normal PETSc code, so the normal KSPCG, and have it the same source, right, using this new API. Have it both be the CPU and the GPU code, and it does the same thing. Well, it does different things depending on the backend, also at runtime. So would it be faster and, of course, preferable for us to use the vendor-specific ones? Yes, but then we lose all the customizability. So I think, I don't want to say no, but the point is not necessarily here to maximize the actual speed here. It's mostly to keep the code the same, but also to increase where we can and keep the same PETSc customizability and paradigm.
And if you take a look in the KSP header file, you'll see that something as simple as KSCG, we have several implementations. And if we want to add a RockM implementation for when you have that available, that's a perfectly acceptable thing to be added to the PETSc library. Yeah. All right, let's thank Jacob one more time. Thank you, Jacob.